Okay. Yeah. Okay, we are recording. Hello, everyone, and welcome to the third session for this course, uh, Programming Data Structures and Algorithms using Python. Um, again, so my name is Raj. I'm a PhD student in IISc. And in the last session that we did on 8th August, so we covered the quiz 1 and 2 and the programming assignments, assignment number 1 of week 2, sorry, right? And in that, we had discussed a few versions of this solution, prime product, the first question. So it seems like some of the versions are not right, so I'll fix that today, and then we'll get into any doubts you have for week 3 and week 4, if you have watched week 4 lectures. Okay. Um, so before that, can someone confirm that you're able to see the video links on YouTube, etc.? Is that is that is it all okay? You're able to see the files that are uploaded for every week. Um, you have not checked, or okay, fine. Okay, you're able to see. Fine. Okay. Um, okay. Uh, Fine. So we'll discuss the first programming assignment again from week 2. All right. Um, what is the Yeah. So um, okay. Again, the audience might be a bit different, so we'll just do it from lectures are played when used YouTube directly, but within app it doesn't. Which app are we talking about? Swayam app. Uh, okay. This might be something that NPTEL might have to look at. But yeah, I think as long as you're able to look at it in YouTube, hopefully you're able to at least getting the content. Um, okay, so uh, again, so we'll start the first. We'll do the first question again. So in this, what we need to do is we need to write program which basically checks whether a given number is a prime product or not. And the way you define a prime product is that if it can be written as a product of two primes, which makes sense. Let's say if P and Q are both primes, then P into Q would be a prime product, right? Um, so when you to write a Python function that is prime product of M, and which takes integer M as input and returns true if M is a prime product or false otherwise, right? Uh, if M is not positive, your function should return false, right? So this also we need to incorporate. Um, uh, right. So before we get into what solution we had last time and what is the improvement, etc., uh, um, anyone wants to tell what could be the good approach to solving this? Any approach that you might have in mind? How would we solve this question in through programming or through even in intuition? Let's say if you had to think about it, how would you go ahead and solve it? Okay, auxiliary functions, factors, and prime. So what do these auxiliary functions do? So you can unmute and talk, not a problem. Uh, okay. So so the idea is, if we had to uh, think about this, so let's say we have a number, let's say m, right? And the idea is that we'll list all the factors of m, right? And then let's say factors of m could be, again, 1 and m are always the factors of any number. And then we look at multiple other factors of m, right? Could be any other set of factors. Uh, Here, the idea is that whenever you find, let's say some factor is a prime, let's say this is a prime number p. Now, this is a factor of m. So if I divide m with p, I would get another integer, right? And let's say we'll call that as q, right? So then, therefore, p into q is m. So now, in this way, I can get for every factor, I'll get the corresponding number which I multiply with to get m. And then basically checking if both p and q are prime, will basically solve the problem, right? This is exactly what we did in the first iteration last time. Uh, uh, right. So in this case, so let's say we'll define the function like this: prime product of m. Okay. Um, and for every so factors will basically be from range of, let's say, 1 to m plus 1, because m is also a factor, right? Now we check if a number is a factor of another number. I mean, the by definition, the remainder will be 0, right? And for remainder, we use the percentage operator, right? So percentage symbol. So if m percentage I is equal to 0, so uh, this means that I is a factor of m, right? Uh, if that's the case, then I need the corresponding number, right? So let's say if this is a p, I want the q, which when multiplied with p gives me m, right? So that you can get by integer division, right? M uh, double slash I, or floor division. That is basically j, right? Now, what I need to do is I need to check if, uh, so let's say if I have a function which tells me whether a number is prime or not, right? So we'll implement this in a bit. So let's say this number is x, right? So this, what it will do is it will return true if x is prime. Okay, so we'll write that function in a bit. And the idea is that if both I and j is prime, then we are done, right? Then it is surely a prime product, right? Otherwise, so if you're not able to find any such, um, factors which satisfy this condition, we would return, let's say, false, right? Now, what's pending is how to implement the is prime function, right? Now, in this case, what will happen is that we know that for a prime number, the only factors are 1 and itself, right? So we can basically check. So for I in range of, so any number between 1 and m minus 1, oh, sorry, x, right? Uh, if it divides this number, let's say x, then for sure it's not a prime, correct? So what we're doing here is we're saying I will go from 2 to x minus 1, right? All the integers from 2 to x minus 1, because we know that for any number, 1 and x will divide that number, right? So 2 to x minus 1, if I go in that list or in that sequence of numbers, if any of the numbers divide x, then for sure it's not a prime number, right? So otherwise, they'll return it as true, correct? So this is sort of what we did last time in version 1. Okay. Now we can make it a bit efficient in some sense, in the sense that um, so we discussed last time that for a prime product, um, the only factors that if M is a prime product, let's say if M is a prime product, right? Then the factors of M will only be one, let's say P, Q, and M, right? There is no possibility of any other factor for M, for M, if M is a prime product. And last time I made a wrong assumption that if this is true, then this is so if there are only four factors, then it's a prime product. That's not true, right? So here, the idea is that it will have only four factors, one, P, Q, and M, right? Now, how can we use this idea to make our code a bit more efficient? So because here what we're doing is we're going through all of the numbers. I mean, the code is such that it goes through all of the numbers and it checks whether the first one, first factor, whatever the factor it gets, and then tries to check it's a prime or not, and so on, right? So is there any way to make it a bit more visually, at least better, by using this fact that we have four factors, and uh, it will always be in this form, right? Any thoughts before I get into it? Any thoughts how we can use this idea? So one thing that I can think of is uh, let's think about this idea that, let's say, what is the smallest factor of any number, right? Any number, smallest factor is one, that is fine, other than one, right? Smallest factor that is greater than one. Uh, will this be prime or not? That's my question. So any number you take, the smallest factor for that number, uh, but again, more than one, will that be a prime number or not?
Yes.
Any thoughts?
Suppose 2 is prime number. 2 into 3,
Right.
6 is also prime, the product of two prime numbers.
Correct. No, that is fine. So that's a prime product. But I'm saying in general, the smallest factor for any number will more than one will be a prime number. Is that okay?
Yes. Could be.
No, 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 not could be. So can you think of an example where it is not true?
No, no.
The one who said could be.
I said could be. Say 3. 3 could be a factor. But 3 is not the smallest number, right? 2 also is smaller than 3.
No, no, smallest factor. So let's say you list down all the factors for a number and then
Hmm.
look at the smallest number among them. So
Okay.
I'm not saying the smallest number in integer in the whole of integer list, which is basically two, more than one. That has to divide. I'm not saying that. I'm saying you list down all the factors for a number, right? What all
Okay.
factors exist? In
Yeah.
that list, in that list, the smallest factor has to be a prime. Is that okay? Would that be an incorrect
Yeah.
assumption or not?
Yeah. Yeah. Everything will be, mean every number can be written as product of primes.
Product of primes, exactly,
Yeah.
right? Yeah. So the smallest factor would be a prime number, correct?
Yes.
So,
Yes.
so basically, if I were to, let's say, iterate from this in this version, let's say 2 of m, right? So now what I will do is I will iterate in this range, that is 2 comma m. Okay. Uh, Now what I want is I need, so whenever the first number, the first time I get a factor for m, I will break out of this loop, right? The break, right? So at this time, so if it is broken out of this loop, right? Then I is a smallest factor of m, which is also prime. Okay. Now, and so by the way, so for prime numbers, what will happen in this case? What will this loop do for prime numbers? If m is by default a prime, let's say if I pass m as 3, will this loop break because of this condition anytime? No, right? Because if m is prime, then no number between 2 and that m minus 1 will divide that number, right? Will be a factor of that number. So here, if I do else, uh, again, everyone remembers what for else is, right? So if it's terminating in a normal way, this particular thing, that means it's a prime number. We can just directly return false here. Prime numbers are not prime products, correct? So now, if it has come out of this loop in this normal way, so then that means that it's I is the smallest factor of m and therefore prime, right? Now we know that uh, prime product will always have only four factors. Now we know that 1 and m are factors, and we have found a p. We have found a prime factor already. The only thing that remains is that you need to check whether its corresponding number, the one that you multiply with m, is that prime or not, right? So basically what we're doing is we are getting rid of this idea of is prime of I, because we know that for a fact that I will be the smallest factor for any number is a prime number, right? So then now I just define mj is m uh, multi, floor division of I, and check if j is prime or not. That's it, correct? And if that is prime, then you can return true. Else, you can return false. Is this clear? And this is a problem that we had found out last time. So some Milind, I'm not sure if he's there in the class, but Milind had pointed out, right? So let's say number like 8, right? So 8 factors are 1, 2, 4, and 8, right? So even though so smallest factor is all obviously prime, that is fine. Its corresponding number also has to be prime. Only then it's a prime product, otherwise it's not, right? So this sort of thing checks for that exact condition. And we don't need to iterate through all the factors and everything. We just need the first smallest prime factor, first smallest factor, which is by default prime. Does this make sense? Any doubts in this implementation? No doubts. Okay. Okay, I think that everybody has understood. Uh, Okay, somebody said dry run. Okay, we'll do the dry run once then. And explain once again. Okay, fine. So first, uh, first thing we need to agree upon is whether this is true. So Bhavya and others also, can we confirm that this is true or not? Is this clear or not? Whether the fact that if M is a prime product, then the only factors that M will have would be M, sorry, 1, P, Q, and M, right? Is this clear or not? So let's say, for example, so we discussed this last time, but let's say, for example, we are looking at 36, 36 as a number, right? So here I can write this as 3 into 12, right? Now, because 12 is not a prime, I get other sort of factors coming in. That is basically I can write this 3 into 4, and then I can multiply, I can put this 3 and 3 together, and I can write this 9 into 4, right? But when I say, for example, 6, I can write it as 2 into 3, right? Now 3, I cannot break it down any further because 3 is by default prime. So if I say it is 1 into uh, 3, right? 2 into 1 is again 2 only. So I don't get any other way of breaking down the number other than it's it's two prime factors, right? The one that is trivial, of course, is 1 into 6, right? Which is true for any number, regardless of any properties, right? Which is true for this also. 1 into 36 is always 36, right? So therefore, if I were to list down the factors of 6, I would get 1, 2, 3, and 6. So always any prime product will have only 4 factors, 1, P, Q, and M. Okay. Is this part clear? Okay, fine. Now, so if this okay, let's say this is clear. Now let's think about this idea that the smallest factor for any number which is greater than 1 will have to be a prime number. Okay. Yes, go ahead. Somebody had a question. Okay. So the smallest factor for any number greater than 1 has to be a prime. So let's say um, so let's say when I was if I were to list down the factors of 36, okay, in this case, what all I would get? I would get 1, 2, 3, 4, 5, 6, then starts 4 into 9, 3 into 12, 2 into 18, and then 36, right? So this is how I would get the factors of 36. Now look at in this list, which is the smallest one, uh, which is also more than 1, that is 2, right? And we know 2 is a prime, right? So the idea is that any smallest factor of a number which is greater than 1, this would be that factor, that number that we're talking about, the factor that we're talking about, that would be a prime factor. Now you can also do this a bit formally. You can say, oh, assume that it is not, assume it is not prime, and then go ahead and prove that this assumption is false, right? So that's called as proof by contradiction. Again, straightforward stuff here, but uh, uh, is it clear intuitively? Is this idea clear?
Assuming it is not a prime, still you can break it into prime factors further. So therefore,
Exactly.
therefore, finally you will end up with only smallest prime only.
Smallest prime only. That's exactly the idea, right? So in this proof, the simplest thing is, let's say it is not a prime. And then you will say, okay, if it's not a prime, then it can be broken down into another small factors, right? Because if it's not a prime number, so then you will say, okay, let's say it is some a number m. Okay, let's not use m. Let's say it is some number, let's say n, right? And because it's not prime, I can break this down into another some number, let's say p into some other, let's say q, right? Because which is let's say p can be a prime. Now p is a factor of n, so p is obviously smaller than n, and p is since n is a factor, p also will be a factor. I mean, and p is smaller than n, right? But we said n is the smallest factor, which is not which is against the uh, uh, what we have assumed. So hence that is a proof by contradiction. Again, don't worry if you've not followed it, it's fine. Um, but intuitively, does it make sense that the smallest number would be a prime number, right? So with this now, we will now combine these two ideas together. That is these two, right? So point number one and point number two. Okay. So now what we're doing, we said 1, P, Q, and M are the um, four factors of a prime product. 1 and M we know. Trivial case, no, don't to worry about it. Let's say P is less than Q. So P is the smallest factor. We know P is prime. So what remains is only the fact that you need to check whether Q is prime or not. That is it, right? So for this, so this problem now becomes into two steps. First is find smallest factor. Okay. Then check its corresponding number, that is that you get when you multiply and get m, is that corresponding, let's say, multiple, is this is prime or not, right? So find smallest factor, that is like finding the value the value of p, right, in our for list of four numbers, and this corresponding number uh, is basically the q, and we're just checking whether q is prime or not. That's it. Okay. So that's exactly what we've written here. We're saying that for I equal to in range of 1 to m minus 1, right? Again, remember, range will go in this case from 2 to m minus 1 inclusive. It will go from all the way from 2 to m minus 1. Now, wherever the first number that you find, it's a factor, that is the smallest factor, right? By default, because we are increasing I in ascending order. So whichever the first number that you find is a factor of m, that would be the smallest factor. And to check a factor, this is the way to do it, right? That is basically the remainder is zero. If remainder is zero, then I is a factor of m, right? So you break here. So when you break here, basically, I whatever I value was here during this loop condition, I stays there, right? I will not change after it. That's why we are breaking from the loop here. Okay. And then here so here this case, the else case, is basically when m is by default a prime. M is itself a prime. So let's say if it is some 7, right? So you will not find any factor between 2 and 6, of course, right? Because m is a prime number. So in that case, you will say, okay, return false, because we know because it's a prime number, it's not a prime product, right? Now, once you do that, uh, uh, in case of, for example, let's say when m is 6, then what will happen is you will break when you find 2, and then you will find here as 3, and you'll check whether 3 is prime number or not. Okay, so we'll go through, we'll run this code for multiple numbers just to drive home the point. Okay. So first, let's say we'll do simplest case of 6. 6 is a prime product. We know that, right? So uh, yeah. So let's just do that. Huh. So first M is 6, right? Then we go inside the loop. So for I, we are saying I should go from 2 to m minus 1, right? So first we say I is 2, right? And 2 is a factor of 6 or not? It is. So we come here and we say this condition is true and you have to break from the loop. So when you break, what will happen? This whole set of statements will be skipped after this, whatever is here, right? And I will not be changed after this. It's going to come out at this line of code, right? And it's come here, and you can see I is remaining 2. That's important. That's why we use the break command here. Okay. And then when we come here, we say, okay, m is less than I, right? Sorry, m is you divide m by I to get the integer a portion that is 3, right? So 6 floor division by 2 will give you 3, and then we check whether 3 is prime or not. So that you do it again in this form. So you will go here and you will say, okay, so in this case, what will happen is x is 3. In this particular loop, I is going from 2 to 3. Uh, and here, there's only one number, that is, it checks for 2. So 2 doesn't divide 3. Therefore, you will return here as 3. Okay. And you would come here, and therefore, this is true. So you come inside the if condition and you say return true. Okay. Uh, does this help? Okay, so then let's look at other examples, other cases. For example, let's say if we were to pass a prime number itself, right? So then, uh, yeah. So 3 is a very small. Um, yeah. So here, yeah. So here, first I will start from 2 until it'll go until 6. So you can see that this will never break out of it'll never enter this condition because none of the numbers are going to divide m. So first, so here I just see this particular value, I is 2, right? Then I is okay, I has come here. Yeah. So then I is 3, 4, 5, and now I is 6. That's the last number that it will try, and it say, okay, it's not dividing again. So then it will come down to else part, right? So because the loop has finished in a normal in a usual way, that is, it has gone through all of its values that it was supposed to go through, right? And then so therefore this means that there are no numbers that divide this number m in this range. So therefore it's a prime number, and prime numbers are by default not prime products. So you can just return false here. Okay, it'll return false. Uh, then let's do, for example, another case um, where we know it's not a prime number. Let's say 36, for example. Um, or let's do 50. No, 45, right? So yeah. So first I is 2. I doesn't divide m. 2 doesn't divide 45. So we'll then continue the loop and we'll go and we'll see I is equal to 3. So I is equal to 3. So 3 divides 45. It'll come inside, it'll break the loop and it'll come here, right? And it says 5. So I is the smallest factor of m, that's 3. And then divide 45 by 3, you get j, which is 15, right? So now we go and check whether 15 is prime or not. How do you check that? You come back here and we see that in this range, that is 2 to uh, uh, you know uh, uh, 15, right? You found a number called 3. I is 3, and that divides 15. So hence it's not a prime number. So it would come back here and it'd say, okay, this is false. So it goes to the else part and say return false. Okay, so we have checked 3 conditions. One is a prime product, a prime number, and not a prime product, neither prime number. Okay, any doubts here? No? Okay. Um, okay, perfect. Yeah, and others, I mean, we have discussed last this one, quite straightforward in that sense. So, just please go through the video. So we'll move to week three. Week three lectures. So two things were taught here. One is about, how to break out of the loop. We, for example, use that break command in this case, in our case also, and then uh, binary search and some notions of efficiency and two sorting algorithms, that is selection and insertion sort. So any doubts in any of these conditions, you can raise your hand, or uh, you know we can go through that to your doubts one by one. Any doubts? How to use search algorithms in practice assignments, like we did now? We didn't use search in this, right? Um, so the doubts are basically the concept names in the in the videos. Um, okay. Uh, shall we do the binary search then? I can tell what's the just a moment. Yeah. Um, Binary search, shall we do like a dry run sort of a thing? Would that help? Yeah, this sort of a thing, right? So before that, week two assignment, second problem. Again, see, we have covered week two quiz, week one quiz in the last video. So I would suggest please go through that. Unless you have a very specific question, please, we'll do that. Okay. Um, okay. So in binary search, what is the idea? So let's say if we have a sequence, value left and R, uh, yeah. Mm. So can we do binary search on unsorted arrays? Anyone wants to answer that? No, right? Because the whole idea in binary search is that if you have a sorted array, then you can basically um, you know um, uh, make do a more efficient version of your search, right? Which is basically just looking in parts of the array without having to go through the complete array, which would be the case in case if you were to go through uh, if you have an unsorted array. Yeah. So here, sequence, that is SEQ, is basically some sort of a sequence which has the elements in sorted version, right? So we'll have to ensure that when we are trying to run this function, otherwise we'll get incorrect um, you know output, right? Um, then return v search, same sequence, v l emit, else we'll just put that mid plus one, right? Yeah. So- okay, so here seq is the sequence that you have in that you have. V is a value that you're searching in the array. Yeah. Um, so yeah, so V is a value that you have in the array. And so V is a value to search. Okay. Then L is the left index. That is basically in binary search, the idea is that you want to look at one part of the sequence that you're given. So that would basically be which part. So you're defining that part by its endpoints. So left and right. Okay. So it's the left endpoint in some sense, and R talks about the right endpoint. Right. So now let's do this bit interactively. Um, yeah. So let's say you have binary search. So now, in case you have a sorted array, right? So basically, you're given a it's given that all the elements are in ascending order. By the way, this has to be true. It's ascending order, right? Then first, so let's say you want to search a value called v in this sequence. This is a sequence. Now you would basically say you would basically compare v with the middle element. Okay. Uh, Now if v is equal to the middle element, we are done, right? So we found that the element is in the list in the sequence, right? So that is this condition, right? So line number 12 and 13 basically do that. It's saying that if the value that you want to search is exactly the middle element, then that would be the then you can just say it's true, right? Otherwise, so in case it is not the middle element, and we know for a fact that the numbers are in ascending order, so then what we can do, we can say that, okay, if v is uh, less than this element, right? So that means v has to lie in in this part of the sequence only, right? So if v is less than the middle element, right? Which makes sense, right? If v is present, then it will be present here only. If it is not present here, you can be sure that it won't be present in the list at all, right? That is the point. That you get that guarantee you will get only because of the fact that it's the sequence is in ascending order, right? So now, so if that is the case, then basically what I need to do is I just need to search in this part of the list, only in this part of the sequence, right? So therefore, it is like saying that I want to search for V. So search for V in the left half, right? Left half of the sequence. Okay. Uh, Now, again, think about it. Because the whole sequence is in ascending order, the left half of the sequence is also in ascending order, right? So it is equivalent to saying do the binary search, right? I mean, I can do binary search for V in the left half. This is the key. This is the idea that you need to understand in terms of recursion also, right? Basically, what we're saying is when you're trying to solve a problem, if you can represent the problem in a same way, but in a lesser amount of, let's say, lesser or a different portion of the problem, right? That is basically the idea that we're using here, right? So we're saying that if the element is found in the left half, then it's present in the sequence. If it is not present in the left half, then it's not present in the whole sequence, right? That essence is captured in these two return statements. So if V is less than sequence of mid, that means V will be present only from the whichever was the left index, left endpoint to the mid endpoint, that is current wherever you were, right? If it is not, if it is greater than that, then it would be present in the right half of the sequence, right? And whatever this function returns, whichever branch I get into, whichever branch I get into, that if that tells me that it is present, then the answer for the main function is also same as this answer which is coming from the different halves of the problem. Okay. Um, so let's look at this in action. So let's say B search, right? Um, it needs four inputs, right? First, a so simple. Okay. Um, and yeah, the value I want to search for, sorry, yeah, value I want to search for is, it says 0, right? 0 we know for a fact is not present here. Um, now, uh, so if this is the case, now tell me what will be the uh, uh, initial call to this argument. What is the left endpoint and right endpoint when I'm first trying to call this function? What happened? See, B search as a function is going to search for the value V in the sequence SEQ, right? Between these endpoints, between these positions in that sequence. Okay. So when I'm first calling the function, what will the left endpoint and right endpoint, what should it be? 0 and 9. Is that correct? Do others have any comments about it? Right. L is 0, right? And R will be 9. Because they want to say you're searching the whole list, right? And we have 10 elements. So the left obviously is 0. That's Python convention. And the 10th element will have the index of 9, right? Again, by Python convention. So again, so we'll say from 0 to 9 inclusive, you search in this particular list, right? So let's see what's happening. Um, Yeah. So first we check if r minus L is 0, we'll come to this condition when this condition will be reached, right? And might be reached in this example. So if r minus L is 0, let's skip that for now. So first we want the index of the middle element. That is just basically going to be L plus R by 2, right? So in this case, our case is going to be 4, right? So 0 plus 9, that is 9. 9 by 2 is 4.5. Floor division gives you 4. Now, what is the sequence of mid here? Sequence of mid is 5. And what we want to search for is 0. So 0 is not equal to 5. So that means we are not sure. So the middle element is not the value that we were trying to find, right? So then we go and check here. Now we know that 0 is less than 5. So it basically makes sense to check the left half of the numbers, right? Uh, oh no, no, 1 second. Here, mid has to be, sorry. Uh, so here I think the the implementation requires you to say, yeah. Okay. Not 9, it'll be 10. Again, remember in the convention of range function sort of thing, right? So you will take, uh, you want inclusive of all of these. So you will tell one number extra, one number greater than the number of elements that are present in the list, right? So you have 10 elements here. So 9, index 9 will be the last element. 10 will be the right index that you want to stop at. Okay. I will just start again. Yeah. So, so in this case, now we are saying that if V is less than sequence of mid. So now I'm saying do the binary search for the sequence in the left half, right? So for that, what I will say you look at only until 5, right? Until the index 5. Uh, sorry, until the index 4, right? So left is 0 and mid is going to be 5 in this case. So again, you can see here in the in the call thread, we're going to call this function recursively. So I will this function will be called again. So as you can see that we are now in the same function, but in a recursive call. And now you can see what the values are. Sequence is the same, which makes sense. V is same, which makes sense. Left is 0, but right is 5, right? So we're saying you search from 0 to 4, inclusive of 0 to 4, right? Okay. And then we continue. So now in 0 to 4, what is the mid index? That's 0 plus 5 by 2. Um, that's what 2, right? Mid is 2. And then again we check whether what's the relation between V and sequence of mid. So sequence of mid is now 3. So 0 is not equal to 3 and 0 is actually less than 3, right? So again, we call the same branch, but now with this particular values, that is left is still 0 in our case, but mid is now changed to 2, right? So we'll have again a third recursion, right? So we're going to third depth in this case. So as you can see here, third depth here, right? Then again, left is 0, right is 2. So we're saying look at the first 3 elements, 0, 1, first two elements, right? And then what is mid again is 1, right? Um, this becomes so V is less than C. So again, we'll check uh, sequence of mid in this particular uh, form. So sequence of mid is 2. 0 is less than 2. So search in the again in the leftmost half, right? Uh, again, come back here. Now, again, we are doing going to do this. That is basically um, uh, R and L are not the same. So now we'll come back here and we'll check whether sequence of mid is what is this here? It's 1, right? And then so 0 is less than 1. So again, search in the leftmost half, right? Right. So now, we come to a condition where R minus L is 0, right? So that basically means that the left and the right endpoint are actually uh, exactly the same, right? That means there is nothing else left to search, right? So therefore, that means we haven't found the element in that in that particular function call, right? So that becomes false. Hence this condition. So when R minus L is 0, that means there is there's nothing else left to search, which basically means that the element is not present in that list, right? So that is what this condition does for you. And then you will so remember again we are in 5 recursions. Okay, so this was the recent most one. The above one, remember, we had run with this particular version where L was 0, R was 1. Aresha. Uh, so I just ran that. Mm, just a moment. Yeah. So we were in this particular above, recursive call. Again, remember this was from another recursive call where left endpoint was 0 and right endpoint was 2, um, which was again the left half of 0 to 5, right? Which was the left half of 0 to 10, right? So then, so each of these, whatever they return, that is being passed as it is to the above to the calling function, which then returns basically the fact that it is false. Okay. Uh, does this help? Is this clearer at least? And then we'll do one more example. Let's say, so this was basically where the value which what I wanted to search was at the leftmost condition, right? So now let's say I will search for a condition, a number which is actually not present in between, right? Something like this, or let me just do 7 and then 8 here, right? So as you can see, uh, and let's make this mm, yeah, right. Okay, so now we have again a 10 elements list, right? Uh, yeah, right, 10 elements list. And what we'll do, yeah, and what we're doing is we want to try and find 8, right? Which should ideally be between these two only. But then it's not present here. Let's see if the program can catch that, right? So again, we'll call with 0 and 10. Um, Mid is L plus R. It's so V is, yeah. So sequence of mid is basically 6. Um, so this is the element 6, and 0 is, sorry, 8 is greater than 6. So therefore it makes sense to search in the right side of the element, right side part of the list, right? So which is basically this 7, 7.59 and 10. So this basically would come here. Okay, does that make sense? And then this call comes here. So, but so you can, at every function call, you can check what is the exact sequence that we are searching in this one, right? So so in this function call, as you can see, we have now reduced our search space from all the numbers 0 to 10 that we had to only this particular search space, that is 7 to 10, which makes sense, right? If 8 is present in this list, it should be present here, otherwise it's not present, right? Um, and then let's do mid is equal to L plus R by 2. And now let's look what is the sequence of mid. Sequence of mid is basically 9, right? So 8 is less than 9, so it should go in the left half, right? So which is exactly where it is going to, right? We're saying that you search from L to mid. So now what is L? Is 6, right? The sixth index 6, right? And mid is basically 8, right? So now when we go into that, you can see here. Now again, when this function call is there, you can check what is the sequence that the model is the program is trying to search between. It's trying to search 8 in this particular list, right? In this particular fragment of the sequence. So again, we'll see what sequence of mid is. It's 7.5, right? Because L is 6 and R is 8, right? So 6 plus 8 by 2 is 14 by 2 is 7, and sequence of 7 is 7.5, right? So now again, 8 is greater than 7.5, so I would search in the right half, right? That's going to come here, and then we come back to this condition, right? So where R and L are both equal to 8. So therefore, so if you were to look at this sequence, let's say L to R, right? This is an empty list, right? So basically we're trying to search number 8 in this empty list, which for sure is not present, right? So therefore, we end up returning false. Okay, and you will get an output as false. Okay, does this help? Um, help you understand what binary search is? Puneet, I can't hear you if you're saying something. Okay, uh, fine. So, what is the doubt in recursion? Somebody asked, there's a doubt in recursion. So, this example also sort of gave you an idea of what recursion is, right? Any thoughts why it's the case? So basically, we're trying to represent, we're saying that the problem can be solved in a smaller version of the same problem, right? So binary search is a classic example where you can see that searching in the list is equal to searching in either half of the lists. Okay. Any doubts on why the searching is in log n? There was a professor did this one, right? Uh, uh, efficiency for binary search. Any doubts in that condition? Why is it log n, order of log n? So this should remind you of your uh, quiz one first question, right? So what we're saying is, let's say whatever work you wanted to do on the list of size n is basically uh, equivalent to doing the work in half the list with some with a function with a function check, right? With some extra additional work, basically, right? And then you can keep on writing this over and over, right? This expand it in this sense. And what you will see is you will end up writing something like this, right? And we know for a fact that so for recursion conditions, such functions, you need to have something called like a base case, right? So let's say that is let's say for example, if n is an empty list, right? Which is exactly what was happening here. So when we hit the condition like when R and L are both zero, it's sort of saying that it's sort of like saying search in an empty list, which we know for a fact that it is not present, right? There's nothing in the list to be searched, right? So T of 0 can be defined as 0, right? So then therefore this will stop exactly when uh, uh, K uh, becomes smaller than log n base 2, right? So it will go up to that level and then therefore this will become 0 plus log n base 2, right? And so therefore the amount of time taken, that is T of n, time taken to solve this problem would be of the order of log, right? So by the way, if I were to uh, do something like ternary search, Okay. Um, Ternary search. So here the idea is this. Let's just hear me out. This idea is this. So let's say like in a sorted array, sorted list or sequence, whatever you want to call it. Now, instead of using just the mid, right? Instead of doing work in left half, right half, I will maintain two sort of things, right? I will say lower and higher. Okay. Um, so updating. Yeah, lower and higher. Okay. So, and then what I will do is, let's say when I want to check some value, let's say V, I will check with the element at the lower. Let's say in our you know convention, it is sequence. So sequence of lower. So I will check this. Is it equal or not? Question mark. If it is equal, then we are done. If it is not, I will check with sequence of, let's say, higher, right? And then now I can do it in a bit more efficient way. No, I can say if V is lower than, if V is lesser than sequence of lower, then it will present only in this half, this part, this ternary, this one third. Instead of doing one half, like in binary search, I can do one third, right? And say if it is smaller than lower, then it will be present here, right? So this condition would be if V is smaller than the lower uh, pointing element, right? Search here if V is in between these two, right? V is lower than the higher and higher than the lower. And search in this part if V is greater than the higher element, right? Um, what do you think will be the efficiency? Will it be better, worse? What? Any thoughts? See, because what I'm doing here is instead of looking uh, at every decision, instead of making it into two halves, I'm I'm choosing not one half, I'm choosing one third, right? So the amount of work that you need to do actually becomes lesser, right? So any thoughts? Will that be efficient, not efficient? What do you think? Ah, come on, nobody has any thought also on this. No inputs. Everything is fine. Everything is unclear. Okay, so take some time, think about this. Try to derive an expression like how this expression is. Uh, okay, uh, so think about what will be the expression for T of n in this scenario, right? What will be T of n? First question. Yeah. What will be T of n? What will be the base case, right? And finally solve for T of n. Whatever you do, solve for T of n and make an argument on whether it is better or worse than binary search, right? And the big O notation, what will this be? Okay. Once you solve for T of n, you will get the question number 5, but question number 4 and 5, then you'll have to interpret in a bit different way. Okay. Uh, shall we move to something else? Okay. Um, that is correct. That's exactly what I said also. So we'll just do 1/3 of the uh, array instead of half the array, right? Um, so so try to implement. Oh, I've not written that. So try to implement the code. Try to see what sort of um, efficiency comes out of it, right? Um, and see whether it's making sense to what you were thinking about. Okay. I will not do this. Um, you can post it in the discussion forum. Check if you have any if anyone has any thoughts on that, we can discuss in the next class. Okay, fine. So selection sort. Uh, any doubts or thoughts on this? Uh, was there anything that's confusing? So do you understand what the ideology behind selection sort is? Anyone wants to tell what the main idea behind selection sort is? Uh, Again, as I mentioned previously also, any questions regarding the um, you know um, submission of assignments, marks, exams, all of that you can ask on the discussion forum. The course TAs will solve for it. We have no idea on on what are the exact logistics of the course and all of that. So yeah, selection sort. Any thoughts? So basically, the idea is that you're going through the entire list and picking the minimum value, right? Pick the minimum value, and then you use because that's the minimum, we know exactly where it should be placed. It should be placed in the first location, right? Because generally speaking, we ideally want to do ascending or order of sorting, right? Then once you know exactly where that it's to be placed in the rest of the list, you again find the minimum and put it in the right place of that put it in the second location in the list, right? And that's exactly what the function the code will show, right? So basically the idea is you're saying that go from, let's say, the first first element until the last, um, for every location. And the idea is that once uh, then from that particular start location until the end, you go through all the whole of the slice that you have and find the location where the minimum value is present, right? And then put that minimum value, whatever you had, in the location that you know, which is basically the value start, right? And that's exactly what's happening in selection sort, right? Um, and in the analysis, basically, the thought is here, uh, when you're trying to do for the first iteration, you will you will go through the entire list. That is, you will look at the all the elements in the list. So that's basically n comparisons that you're doing, right? Once you have clarity on the first minimum, which you got, and you place it in the first location, the rest of the list is what you will scan for finding the next minimum, right? So that's basically searching for n minus one. Sorry, you, you will now do n minus one comparisons, right? So therefore, the number of comparisons will here be n minus one, and so on until the last minimum, which is the maximum in this case, which will be placed at the right location, right? So this sort of a summation is going to give you n into n plus 1 by 2 uh, by simple algebra. And that basically becomes order of n square, right? Because this can be written as n square by 2 plus n by 2, which is exactly what the professor also has written. So therefore it's the efficiency parameter is here n square. Okay. Um, does that help? Any doubts on selection sort? And again, in insertion sort, the idea is slightly different. The thought is that you assume whatever the left part of your search space is basically sort of assumed to be um, arranged already, right? And whatever is the next element, you want to find you want to find its right location, right? Where it should be inserted in this particular already sorted array, right? Um, so in that scenario is what you do um, in this insertion sort, right? So where you go from, let's say, some location here, and until you find the right location, you'll keep swapping the numbers, right? And when it arrives at the right location, it will be placed there. And then this particular while loop will stop. So as you can see, for position is greater than n, and then sequence of position is less than sequence of position minus one. So that's basically you're saying from the slice end, you start from there and then you keep going until that you hit the either the first location or uh, you have already been placed in the right location, which will be in this which will terminate based on this particular condition, right? And you're decrementing position, so you're going from right to left in the array sequence. Okay. uh, is that clear? So I'll do so from the next week. I'll do one thing. I'll just have the code of these merge sort, quick sort ready, so we can just do a dry run also by default. Yeah. Um, so week 3 programming assignment. Uh, uh, so for the first question, again think about how you will have like, do you have to maintain the differences in a in some place, or how do you check whether uh, whether the differences are increasing, decreasing? Again, remember, we're saying strictly increasing. So even equality is not allowed, right? So even if the absolute difference of, let's say, 7 and 3 was equal to, let's say, between 3 and 1, then that is not allowed, right? It has to be strictly increasing. Okay. Um, so basically, and second question is a simple, um, iteration. Think about what should be added where and based on what condition, and how you will check for that condition. Okay. Um, and then the last one can be a bit, that will require a bit of elbow grease. You will need to think about how to make the new list, whether elements will always be present in the initial list, and how you will iterate between the two lists that you have, right? So here it's a two-dimensional matrix, which is given as a list of lists. So you'll have to iterate between multiple lists to be able to compute the transpose. Okay. Um, so by the way, do you know why there are hidden test cases? Why not just you know present all of this here, and you can check whether you will get right answer or not? Any thoughts? Any ideas why some things are kept hidden? Oh my. Um, okay. I think nobody has interest to interact. So I'll just mention some, general thoughts on how to do efficiency sort of arguments, right? So this notation that we had, which is written as big O, right? So uh, in the uh, lectures, professor has mentioned it in very in brief passing, but the idea is this. The general definition is this, right? So let's say when you have something, you say a function, let's say f of n, belongs to the big O notation of g of n, right? So if there is some uh, n n naught, right, where for all, yeah, so for all n greater than this n naught, right, uh, f of n is less than or equal to some constant, let's say k into g of n, right? Uh, there exist, can I just subtract it like this? Yeah. For all this one, yeah, there exists a k such that this is true. Okay. So that's why, um, so basically what this means is, let's say you have a n, and you have, let's say this is f of n, right? And this could be g of n, right? So then what we're saying here, yeah, what we're saying here is, let's say there is some n naught here, right? Such that whenever, for all values greater than n naught, right? Basically this part of the graph, right? F of n is less than some constant value of g of n. So f of n is always, so g of n basically upper bounds this f of n, right? So in this scenario, when we had this thing, right? So when we had n into n minus 1 by 2, which was the t of n that we calculated, right? T of n equals to this for both selection and insertion sort, correct? So in this scenario, uh, the idea is that this can be written as, let's say, n square by 2 minus n by 2. Oh, was it n minus 1, n plus 1? I think plus 1, right? N square plus by 2 plus n by 2, right? So now you can always say that this number, I mean, this function is less than, let's say, n square, right? For some, let's say, number where n is, let's say, greater than some 100, right? Because when n grows such large, uh, huh, 10n square, for example, let's say, right? So because when, let's say, n is greater than 100, the contribution of this n by 2 is going to be very small compared to what n square will contribute, right? So therefore, this particular sort of a function will be dominated by what n square, the n square term and not n term as such when n grows larger, right? So we found a k, let's say, for example, 10, and we also have a, let's say, n naught, right? Which is, let's say, for example, 100 in our case, right? So where this function is less than n square. So now this is the function that we had. So we have, this was t of n. So then we say t of n belongs to big O of this function, that is n square. Okay, so this becomes like this, right? So therefore we call it as, so that we say that t of n is growing quadratically in n. T of x is growing quadratically in n. Yeah. So this is sort of useful to understand when we are trying to, so one thing you need to understand, it doesn't matter what the constant term is. Okay. In term when you're looking at the big O notation. Yeah. So we just want a rough idea of its time complexity, right? That is what this tells you. So we don't really care much about the constant term. That will be useful when we are trying to find the exact running time, right? Uh, Between, let's say, two algorithms which have the same, let's say, uh, big O function. Yeah. Uh, and by the way, any thoughts on why this is I mean, why not look at the exact running time in these cases? Mhm. Why not compute the exact running time instead of doing all of this approximations and all that? So the idea is that when we're talking about algorithms in general, algorithms should not be, I mean, how efficient an algorithm is should not depend on its implementation, right? So because only implementation is going to give you the runtime, how much time it took for the algorithm to run on some computer, right? Because that is affected by how, let's say, the programming language is efficient or not, whether the CPU was, high end or not, and so on and so forth. So ideally, when you're developing an algorithm, you would basically use these sort of notations to argue upon its efficiency, right? Because going forward, this can be implemented on a high-end CPU or a low-end CPU, and so on, right? So therefore, that's why you don't look at running time, but rather you try to look at how the function is growing in general, right? And then make arguments about its efficiency and so on. Yeah, that's the idea of big O notations. Um, Anything else you guys want to know? How many of you have gone through week 4 merge sort function? Doesn't seem like people have gone through merge sort yet. So I'll just give you a sort of like a thinking question. So in merge sort, uh, again we use the idea of recursion, to argue upon its, how to use it. So let's say you have a array, right, which is unsorted, right, and you want to sort it, um, right. So the idea is that you will say, I will sort the left half, okay, and then sort the right half. And then because now each of them are sorted, I will now merge the two sorted lists, whatever sequence halves that you have in some way to form the overall sorted list, right? And again, just go through the video, you will get to know what how to do that exactly. So once you're done with the video, just think about this scenario. So let's say instead of doing this half sort of a mechanism, why not do three parts? Same like how you were talking about ternary search, right? Um, Here also, I can just divide it into three parts, right? So I can just say sort the leftmost part first, then the middle part, and then the rightmost part, and then merge them such that you get a sorted array, right? So will this be more? Which among these will be the more efficient version, um, and why? That would be with proof, of course. Um, and what's the proof that you have for your argument? So think about it a bit, and that will give you some way of understanding how to analyze these sort of um, algorithms in general. Okay. Um, any doubts on how to work with loops, lists, etc.? You can let me know. Um, any any further doubts? It may need extra memory. What may need extra memory? The merge sort thing with the three paths. Yes, it may need extra memory. That's correct. So yeah, actually, this brings up a good question. Um, so uh, memory versus time is a very is an it's not a solved problem. I mean, in the sense that should you always prefer high memory or sorry, low memory or low time. Um, but again, in general speaking, uh, your it's sort of said that memory is cheap, right? So you can get, for example, at least the way the industry has been growing, you can get higher RAM, or higher GPU memory or higher RAM memories for lower cost compared to how it was before, right? Um, so hence, generally speaking, when you're designing algorithms, of course, you need to think about memory, but running time is one of the biggest things that you would, try to solve for. So you're right that it will need extra memory because it will need to do recursion at three levels. You have to maintain, uh, you know, uh, do it at a bigger level. But think of it in terms of the running time, right? Uh, the way we are looking at uh, now also in merge sort, for example, or in selection sort, insertion sort, look at what level of work will be done by the computer. So what's the sort of like the time to compute, do your complete task, which is your sorting, right? So in that sense, think about it and see whether you can you know make sense out of it. If you use extra memory, it will also need extra time to read and write. No. Memories, again, it's addressable by the location, right? So it doesn't in general mean that higher memory means you need more time to write and read and write. And generally, we don't consider these sort of interactions when you are looking at algorithm efficiency. This will come when you're trying to design programs or design new language or mm, yeah, design, let's say, uh, uh, yeah, programming language basically, right? So because then the language has to be efficient enough to be able to do that sort of a thing, and how it interacts with the assembly code and the machine code and so on, right? Yep. Merging sorted lists is more efficient than sorting from scratch. That's correct. That's the idea behind merge sort, right? Um, if you already have multiple lists which are sorted among themselves, the merging operation doesn't require as much time as the overall sorting, right? And that's exactly what you will prove in the merge sort analysis, right? So where you come to the order of n log n compared to insertion and selection sort, which is order of n squared, right? Um, and n log n is uh, lower than n squared, so it is efficient in that sense. Yeah. Any questions on week one or two also you can ask lectures. So clearly define the steps. See, I would suggest uh, thinking. So what approach you're taking, let's say um, in your brain to solve the problem. You just need to be able to put that on paper, one after the other, right? And if that is a problem, that you will overcome with more practice, right? So if you feel like the current problem statements, I mean, uh, we just had one programming assignment till now, so you can practice more problems, on other websites and so on. That will help you build muscle for this sort of exercise. So you can find more assignments, I mean, more sort of such sort of questions in things like Lead Code, Hacker Rank, sort of websites where you have algorithmic sort of questions to be solved. And then that will help you build ideas on how to solve step by step and then implement them in, let's say, any language that you want. In this case, it could be Python. Yeah. Sure. So the discussion forum is basically here, right? Q&A. So that is the discussion forum. So you can click that, and there you can post questions about assignments and all of that. Yeah. So in general, when you're talking about dictionaries, remember this that uh, dictionaries basically um, right, can allow anything as a key, which is basically immutable, right? So even tuples can become the key for a dictionary, right? So let's say I can always write D, let's say if D is empty dictionary, you can always write 10, comma 20 and 30 and then assign some value to it, right? Uh, all right. So anything which is immutable. So and again, as you know, the basic types, for example, that is int, int and string and all of that is also immutable. So those will all obviously be allowed, right? Um, let's say hello, right, is k or something like that. Again, the value can be anything. Value can be a list. right? Uh, so this is basically you're trying to map. You have a sort of like a table if you think about it, where is the key and there's a value stored against it, right? And you can index it based on the key, right? So here in this case, it would be sort of like saying that you have a tuple 10, 20, 30, and it's storing A against it, and hello as a key here, and here you have a list 2, 3. Okay. So anything which is immutable or actually in a sense hashable, that uh, that can become a key. Okay, in dictionaries. Um, okay, seems like no further questions. We'll meet in the next session. We'll discuss week 3 solutions, that is programming assignment that would be done by then, right? So we'll discuss week 3 programming assignment and any questions that you have for week 4. Okay. Thank you for joining, and we'll see you next week.